talk voltage dividers. Voltage divider. Okay, so let's talk maybe first about what the purpose of or where you might need a voltage divider. So let's do as an example your fridge. Okay, so the fridge is connected to some power. Essentially, it sort of works like this. Here's your ice box, and inside there'd be a thermostat of some description, right, that you can change the value of, right? You can crank it up or down to whatever temp you want your fridge at. So how does the fridge know when it's reached that temperature, right? Well, you put something inside it called the thermistor, and the thermistor changes its resistance based on the temperature, okay? So at a high temp, it is more resistant, or it has a higher impedance than at a low temp, okay? Less resistant. So what you essentially are going to make is a circuit where you're more or less monitoring what the thermistor says, okay, and you're basing whether the compressor turns on to circulate your coolant through your fridge or not, right? You don't want it circulating all the time, you'll freeze everything. You just want it to kind of maintain that temperature that you're after, right? So how do you set that up? What you would do is you would put your thermostat in here, and you would make it a variable resistor, okay? So a variable resistor, just something that you can dial its resistance up and down, okay? Then you would put a second resistor here, and this is going to be your thermistor. And the thermistor symbol is kind of like the variable resistor symbol, but it's a little bit different. It just looks like that, okay? All right, and then what you're going to do is you are going to pop in here 2 terminals, okay? And we have a voltage here, okay? We can call this R1 and R2. And essentially, what's going to happen here is you're going to set this to some value, okay? And the thermistor is going to change its resistance based on the temperature inside the fridge. And what that will do is it will vary the voltage that is measured across here. This would then connect probably into something like relays or maybe into like a logic chip of some sort that would look at this and say, okay, what's the voltage on here? You know, if that voltage drops to a certain value or rises to a certain value, we kick in circuitry that makes our fridge go, okay? So we might be interested in figuring out what the V out is based on what values of resistance we have on each of these particular resistors. So this is a place where you would use what is called a voltage dividing circuit, okay? What we're interested in, probably in most cases, is monitoring what happens across some sort of changeable resistor, whether that's a thermistor, which is measuring temperature, or a light-dependent resistor, which is maybe measuring how much light there is, or maybe like a strain gauge, which is measuring how much bend there is on something like that. But what we want to know is how do we calculate what V out is? So we call this V in, we call this V out, the area that we're monitoring. And this again would connect probably to some other part of the circuit. These can be kind of used as well. If you say we're to put like an LED across here and have a variable resistor here, you could use it, I guess, as a way of dimming or brightening up the LED. But in general, I do not believe they're used as like a transformer. You don't want to really generally use this as something that's going to run a lot of current through here. So if it's something small like an LED, probably you're going to be okay, but you wouldn't want to try to run a motor on a voltage dividing circuit. There's other ways to do that. Okay, so we know this, right? Okay, and we know that the total voltage drop across both of these resistors, R1 and R2, be like this. Okay. And so that's going to talk about this entire voltage drop. So whatever V in is going to be calculated as I R plus R2. And over here, V out is just going to be I times R2. Okay? And so what we want to do, since this current is going to be the same because these two resistors are in series, is we just want to rearrange both of these formulas to solve for I. So, okay, and we can see this. And finally, you end up like this. Okay, and you can rearrange that any way you need. Actually, you're going to probably more likely see it like just written slightly differently. R2 is on the top anyway, so it's sort of irrelevant how you write it, but you would also probably more likely see it written like this. But these are equivalent to one another, right? But this is just the more common way of writing it. Or yeah, or you could just write, yeah, you could also write it like this. And just before we wrap up here, let's just talk about what sort of sensors we might use in a potential dividing circuit. So oftentimes you'll just have some set value resistor here, okay? And then you'll put your, whatever sensor resistor over here. So types of sensing resistors, we already mentioned the thermistor, okay? When it's hotter, it's more resistant. Oh, I'm sorry. It says it decreases its resistance when it warms up. Let me just double check on that. So the jury's out. Actually, I think possibly what goes on here is that depending on the type of thermistor that you're using, it may become more or less resistant depending with heat, depending what the temperature is, I should say. Okay. So temp, resistance could be like that, potentially, or like this. I do not believe that there's a set rule for that, although please don't 100% quote me on that. Check your specs. Okay, so there's thermistor, there's LDR. Okay, so when you shine light on an LDR, and they look like this, that stands for light dependent resistor. You shine light on one of these guys, it becomes less resistant. Okay, so as the light shines, it really, yeah. So what ends up happening is the light here, right, when it shines on that thing, this is representing the sun, it releases electrons that are able to flow. It would yes, it would decrease the resistance with more light, correct, more electrons are released. And there's this little picture of what an LDR looks like. Thermistor is even less exciting, looks like a little pod. You may also run across strain gauges. Don't believe a strain gauge has its own symbol, but we'll check. And the last one you might see, as I said, is a strain gauge. There's no real symbol for a strain gauge, but it kind of looks like basically, you'd have your input and your output. It'd be a package. Inside, you would see like a whole long bunch of wire attached in there. And if this were to bend, all right, it would change the resistance, properties of this. You could lengthen or shorten the amount of wire, and then in a voltage dividing circuit, you would get that voltage change. And there we go, sensors and voltage dividers.